It's hard to comprehend that there are 2 billion stars in our Milky Way galaxy. On a good night in Theodore Roosevelt National Park, you might be able to count a few hundred of those stars in the night sky. Which of those many stars is closest to us? You might think it is Alpha Centauri at 4.3 light years from Earth. However, our closest star is our own sun at 93 million miles. As children, we always got out a yellow crayon to color the sun, but the sun is all colors mixed together, which gives us white light. This is easiest to see with a sunspotter telescope or from pictures taken from outer space. The sun only looks yellow because the Earth's atmosphere scatters the shorter visible wavelengths. In fact, the sun gives off all the different electromagnetic waves beyond the visible light to include the longest waves, radio, micro, and infrared, to the shortest waves, ultraviolet, X-ray, and gamma rays. To understand how our sun produces light, let's start at the sun's core. The temperature is nearly 27 million degrees Fahrenheit, and the pressure makes hydrogen more dense than gold. The core is where hydrogen atoms collide with enough force to create helium atoms through nuclear fusion. Light, or photons, begin their journey from here and travel through the radiative zone where the temperatures drop to 12.6 million degrees Fahrenheit and the pressure drops down to the density of water. While photons move through the convection zone, hydrogen cools even further to 3.6 million degrees Fahrenheit and is less dense than air. Finally, at the surface of the sun, the temperature has fallen to only 11,000 degrees Fahrenheit. It is at this point that a photon, or sunlight, is released to begin its 8.3-minute journey to the Earth. It takes those photons nearly 100,000 years, on average, to travel from the core to the surface of the sun. This is because of the extreme density, along with each photon's constant encounters with hydrogen atoms. We call the surface of the sun the photosphere because this is where we first see the visible light of the sun. Astronomers need to use a white light filter on their telescopes to reduce over 99% of the light in order to safely view the photosphere. With a quality telescope, you can zoom in enough to make out the granular nature of the photosphere. The surface of the sun is the outer layer of the convective zone. That granular nature is the boiling and movement of the hot hydrogen plasma headed towards the surface where it cools and then falls inward. This is a time lapse of the photosphere, which looks like a pot of boiling water. Recently, scientists have had their closest look at the photosphere with the Inouye Solar Telescope. It is hard to imagine that just one of those granules is the size of Texas. So, what are sunspots? First, let's talk about magnets and magnetic fields. Magnetic fields are best illustrated by watching iron filings surround a magnet. Earth has a rotating iron core, which produces its magnetic field. The sun has a magnetic field as well, but the sun's magnetic field is much more chaotic than Earth's. This is a green-colored computer simulation of the sun's magnetic field, which helps us see the twisted and knotted magnetic field lines. Why is the magnetic field of the sun so different from the Earth? The answer is that the Earth is solid, while the sun is a rotating ball of hydrogen plasma. Hydrogen at the equator of the sun rotates faster than hydrogen at the poles of the sun. It takes 25 days for hydrogen to rotate around the equator versus 35 days at the poles of the sun. It is this uneven rotation rate that, over time, mixes the hydrogen plasma on the sun. The magnetic field lines also get pulled around and twisted up to the point that finally the field lines flip. North polarity becomes south polarity, and the cycle starts all over again. This is a natural 11-year cycle that we have measured for nearly 300 years. Sunspots are directly tied to these magnetic field lines. You can't see a magnetic field line popping out on the surface of the sun and back in, but you know it is there because the magnetic field pushes back the hydrogen plasma around it, which causes cooler spots at the surface of the sun. A sunspot is simply a cooler region on the sun's surface, or a footprint of the invisible magnetic field line, which drops the surface temperature of the sun from 10,800 degrees Fahrenheit to 7,200 degrees Fahrenheit. Let's take a look at the two basic layers of the sun's atmosphere, the chromosphere and corona. We can view the chromosphere with a hydrogen alpha telescope to see some incredible features such as filaments and prominences. Filaments and prominences are ionized hydrogen being pulled up magnetic field lines. The only difference between a filament and prominence is that filaments project out towards us on the surface of the sun, and prominences project out from the side of the sun. They are the same feature on the sun seen from different perspectives. You might be looking at a filament until it rotates far enough on the surface of the sun to be viewed from the side, and then it is called a prominence. Plage is a French word meaning beach. Plage is simply hotter, more active areas of the sun where we see many flares. The corona is the outer atmosphere of the sun that is heated to incredible temperatures. It is where the solar winds of our sun begin. Finally, let's talk about coronal mass ejections, or CMEs, which are often confused with flares. Flares give off energy and are much smaller than CMEs. Coronal mass ejections are when magnetic field lines become crossed, resulting in extreme bursts of energy and particles exploding outwards from the sun. The energy travels at the speed of light, but the charged particles travel much slower and could take 1 to 2 days to reach the Earth. Luckily, our Earth's magnetic field protects us from CMEs. However, some of the charged particles can get through the magnetic field, mostly at the north and south poles. We see these charged particles as the northern lights, or aurora borealis. Finally, we would like to leave you thinking about the immense size of our sun. You could fit 109 Earths across the diameter of the sun. You could fit over 1 million Earths inside of the sun. Here is a simulation representing the Earth in comparison to a sunspot.